Good afternoon. My name is Eugene Bryce of Bryce Energy Services, and I'd like to give a presentation today on solar panels for business, the energy and commercial payback. So recently on LinkedIn, I've seen a number of posts describing new factory units and new warehousing distribution centers. And I commented and noted the lack of solar panels on either roof of these buildings. I thought that given the newness of the buildings and the purpose of the buildings, that it was surprising that no solar panels were installed. Now, whether this is a consequence that the builder is separate to the owner stroke or occupier of the building, I'm not sure. But if I move on, certainly it is possible and readily done to add solar panels to large roof areas. As the construction work is going on, I would have expected it to be far easier to install the solar panels at that stage rather than retrofit over an existing roof. So the economics of building a warehouse type building, modern warehouse distribution center, I'll be honest, not entirely sure, but certainly the costs of installing solar after the roof has gone on would be more than considering solar installation at the time of build. Thereby, you can also integrate it more readily into the electrical system of the particular factory or warehouse or whatever is going on under the roof. So just a quick slide on how solar panels actually work. So solar panels are made out of photovoltaic cells, which are used to generate electricity from sunlight or photons falling on the surface. They are effectively a semiconducting material, which most computers, well, all computers, diodes are made of. And simply from the light falling on the surface, it creates a reverse charge across the junction, creating a DC current to flow. This information on this slide I got from Good Energy, who seem to have a good grasp of the concept. So very simply, sunlight falling on the panels, creating a DC current. How much electricity from one solar panel? So as with everything on the market, you can buy cheap, you can buy expensive, you can buy low capacity, you can buy high capacity. For the purposes of this presentation, we're going to assume that a panel can produce 500 watts per hour, so 500 watts of electrical energy. And as an example, to boil a kettle, which is 2000 watts or 2 kilowatts, you would need at least 8 solar panels. So 250 times 8, 2000 watts, and that would boil a kettle. Bear in mind that the electricity produced from a solar panel is continuous. So it's 2 kilowatts each hour, which is significant for a household. A kettle is only boiled for 5 minutes, so that leaves 55 minutes in the hour with energy to use. So continuing, solar panels rely on sunshine. And the first graph we have here is the output from the panel for a particular time of day. So the peak is at midday or shortly after midday or high sun. And obviously it tails off to zero after sunset. So no sun, no electricity, and worthwhile because of the angle of the sun as the sun rises. It takes a while to get over 80%. So a solar panel rated at 300 watts would very rarely get to 300 watts. Similarly to time of day, time of year. So again, in winter when the sun is low, the output from the panels will be lowest. And again in July when the sun is highest in the sky, the output will be at its maximum. So maximum power output rated middays in July, and minimum power obviously during the night. So the output from solar panels is at its maximum during the summer months during the middle of the day. So a number of factors affect the efficiency of solar panels. First one, and probably the most significant, is the angle of the panels. The best angle for within the UK, and there will be a variance between South England and Northern Scotland, but typically if the solar panels are mounted at a 30 to 40 degrees, the angle of the sun being 50 to 60, so that creates a net or combined angle of 90. So effectively the sun being perpendicular to the panels is for maximum efficiency. Then what also can impact, so similar to time of day, shading and clouds. So you need to install your solar panels with visible horizon. So no trees, other buildings that could impact the amount of sunlight that falls onto the solar panels. And finally, cleaning panels. The surface of the solar panels needs to be cleaned regularly in order to maintain optimum efficiency. How many panels for a 500 kilowatt rated system? So assume each panel is 300 watts, delivers 300 watts. 500,000 divided by 300 watts gives you 1,667 panels. Typical size of a solar panel, 1.8 by 1. So the roof area required is 3,000 square meters. The weight of the panels on the roof, about 33 tons. And the estimated cost of the system is £550,000. So that's installed system panels on the roof. And just as a note from the United Kingdom Warehousing Association, the average size being constructed is 242,000 square feet, which sounds very large to me, but I'll take their word for it. So how much electricity from a 500 kilowatt solar system? Based on the time of day curve and the time of year curve, so you can see on the front axis we have start at January and work our way to December, and on the right axis we have from midnight to midnight. So large swathes of blue where effectively there is no output from the solar panels because it is nighttime. And just to note, this curve is describing the kilowatt hours per half hour. So we have a 500 kilowatt system here. So it reaches a peak of about, let's say, 250 So 250 in half an hour, over an hour, that will be 500 kilowatt hours. So everything's divided by 2 because of the half hourly data. We have therefore a total kilowatt hour production per year of just under 500,000 kilowatt hours, 491,000 kilowatt hours from a 500 kilowatt system. So what we're looking at here is the half hourly data profile for a large business. So this business has a total kilowatt hour per year of 5,236,977 kilowatts, or what we describe as 5.2 gigawatt hours. So just a little bit about this business. It's hotel and leisure, and it has significant winter usage and also significant nighttime usage because guests are staying in the hotel overnight. So it is a 365-day, 24-hour operation. Here we have the same data, but with the energy production from the solar included, or more precisely, subtracted from the import data. And we used the half hourly data from the business in 2019 as an example. So that was pre-pandemic. And now we have a total kilowatt hours per year imported from the grid of 4.7 gigawatt hours, a reduction of 9.4%, which is not bad. It's considering that the system is exclusively daytime energy production, and this business obviously has significant nighttime usage as well. If the business was solely daytime operation, then that reduction would be significantly more, obviously. If the sun is shining and your business is operating, then you'll maximize the solar energy. So just to have a slightly cleaner graph, this is a 2D version of the half hourly plot. So again, along the bottom of the axis, we have from January 19 through to December 19. And this profile shows both the red, amber, and green consumption. And again, total consumption through the year, 5.2 gigawatt hours. Now, if we show the profile with the solar system, again, total kilowatt hours, 4.7 gigawatt hours, reduction of 9.4%. And if we just focus on the region in the summer months and also the yellow section, or amber section, I should say, the majority of the reduction is in this area and associated with the amber period, which is typically between 7 a.m. and 4 p.m. And then we have a little red period between 4 p.m. and sunset. Now, depending on the time of year, obviously in the summer, the greater production, the red period can extend out to 7:30. And if the sunshine, then that would obviously benefit the red period. But not many businesses are still operational after 6 p.m. So energy and commercial summary. So here we have in the middle of the chart, the actual kilowatt consumption in red, amber, green periods, the triad periods, and below we have the actual cost of the electricity in those periods. So if we do a quick zoom in, so along the top here we have night and day. So the grade line is the current consumption or the baseline consumption in 2019. So this business uses 962,000 at night and 4.2 gig during the day, of which 2.3 is in the green period. Coincidentally, 2.3, very similar numbers in the amber period, and in the red period, 613. And the triad is the kilowatts during the triad period. So that gives a total consumption of 5.2 gig. Below we have the generation by the solar. And again, at night, there is 0 generation. During the day, we have 490,000 kilowatts, of which 138,000 is in the green. In the amber, 323, and finally in the red, 29,000, to give a total kilowatt hours of 490,000. So subtracting 5.2 from the 0.4 gives us a net annual consumption of 4.7 gig watt hours. And below we have the time of day charges. For, again, in the grade line, we have the time of day charges for the existing consumption. To note that electricity costs more in the amber period and significantly more in the red period, and also triad charges. Now, if we look at the energy saving produced by the solar farm for each of these periods, we can see during the day it saves 33,000. It saves £100 in the green, 1,279 in the amber, but almost £3,000 in the red per annum. Now, if you look at the consumption in the red relative to the price in the red, you can see that any savings of red period energy are significant. So continuing, if we just look at the percentages at the end, so again, the total daytime saving is reducing by 11.5%, giving it a net, in the green period it's down 6%, in the amber 14%, and in the red 5%, well 4.7%, gives a total net reduction of 9.34%. And in the cost of electricity, it gives a net reduction of minus 8.6%. So you can see that it has no impact on triads because triads occur in the winter and the solar system isn't actually producing anything. So a simple return on investment calculation, assuming electricity price inflation of about 5%. We have a capital cost of 550,000, a net present value of 847,000, internal rate of return 15%, return on investment 154%, and a payback period of 9 years. So in terms of installing solar at a business, questions to consider or comments to consider: how long does your business allow for return on investment? Is 9 years too much? following, how long do you plan the building being operational? So if you're owning a large warehouse, do you expect it to be operational after 9 years? And finally, given the electrical savings for this particular business from that solar farm, that equates to 125.4 tons of CO2 saving in carbon footprint per year. So there is social and environmental considerations as well. So just to conclude, hope for the future is that we move from new builds that look like this, completely blank, to buildings that are black with solar panels. I think it's reasonable to expect that most of these buildings will be here 20, 30 years, and that having solar will add to your carbon credentials and also provide you with real cash and carbon savings throughout the year. Just by way, I tried to count the number of panels on this particular unit, and I think I got to about 16 ridge to gutter and 75 along the length, which at 300 watts gives us a system of 360 kilowatts. Now, we've been talking about a 500 kilowatt system, so let's say an extra third on this, or certainly if the roof in front was covered equally with panels, we'd easily reach a 500 kilowatt system. So if you're about to build or have such a building, highly recommend you speak to your local solar contractor and understand the specifics for your building. And frankly, no reason not to go out and install a system. Energy prices, energy exporting, all in flux. There may well be grants available to support a build in your area. Always worthwhile speaking to your council, local district, see what grants are available. But certainly your local solar contractor will be fully aware of any financial incentives. So that was a presentation by Bryce Energy Services. If you would like to contact us, feel free to email me at info@bryceenergyservices.com, or feel free to follow us on LinkedIn, YouTube, or Twitter. Thank you very much.